I recently made a video on the Sutherland-Hodgman polygon clipping algorithm, and while I was explaining my code, there was this small function called segment intersection. At the time, I felt like I didn't explain it clearly enough. And that bothered me, because this tiny function is actually doing a lot of heavy work behind the scenes. Functions like these are the building blocks of so many bigger algorithms. Clipping, collision detection, vector graphics, Boolean operations, you name it. And even though the code looks simple, the maths inside can feel confusing if you've never touched linear algebra or basic geometry before. So in this video, I'm going to slow down, simplify everything, and break this function apart step by step. So, before we start, I hope you have a tiny bit of background in linear algebra. Nothing crazy, just enough to follow along. So, this function is all about finding the intersection point between two line segments. Let's say the first segment goes from point P1 to P2, and the second segment goes from P3 to P4. To tackle the math, we first rewrite the line from P1 to P2 using something called the parametric form. It looks like this. Now you might be thinking, what exactly is this parametric form? Don't worry, it's actually very intuitive. The idea is that this formula lets us describe every single point on the line segment using just one scalar number t, which we call the parameter. We break it down into two parts. First, the starting point. We first start right at P1. Second, the movement. We move in the direction of P2 minus P1. This is our direction vector. Third, the parameter t controls how far we travel along that direction. You can think of P1 as your starting address, P2 minus P1 as the path you walk, and t as the amount of time you've been walking. P of t is simply your current location. As t changes, the point moves along the line. When t equals 0, you're exactly at P1. When t equals 1, you reach the endpoint P2. When t is between 0 and 1, you're somewhere in the middle of the segment. Okay, so now let's use this parametric form to define both line segments. Segment 1, P1 to P2. Segment 2, P3 to P4. The intersection happens where both equations give the exact same point in space. P of t equals Q of u. Now let's rearrange for variables t and u. We have this equation. Let's move the terms around to group the variables on the left. To make this cleaner, let's give the direction vectors and the offset vector short names. Let v equals P2 minus P1, direction of segment 1. Let w equals P4 minus P3, direction of segment 2. Let r equals P3 minus P1, vector from P1 to P3. The equation simplifies dramatically. T dot v minus uw equals r. This is a system of two scalar equations, one for the x components and one for the y components. But there's a neat vector trick to eliminate u immediately. We use the 2D cross product. In two dimensions, the cross product is not a vector, but a scalar defined as this. We take the cross product of both sides of t dot v minus u dot w equals r with the vector w. Now let's do the step-by-step simplification. First, distribute the cross product. Second, factor out the scalar terms t and u. Third, apply the fundamental property of the cross product. A vector crossed with itself is the zero vector, or zero scalar in two dimensions. This happens because the angle between vector w and itself is 0 degree. The term with u is now completely gone, leaving us with this. We can now isolate t by dividing both sides by the scalar. We now plug in the 2D cross product definition. The numerator becomes this. The denominator becomes this. And that's exactly the formula for t we compute in the function. Now we are in the final steps. First, we use this calculated t and plug it back into the equation to get the intersection point. Second, we then check if t is between 0 and 1. This is the crucial step that confirms the intersection lies inside the first line segment. A similar process, crossing with v, would give us u to check the second segment. The most important term here is the denominator. If the cross product of two direction vectors is 0, it means the vectors are pointing in the same direction or exact opposite direction. In other words, the lines are parallel. So, when we check this condition, we are simply checking if the lines are parallel. If they are, they will never meet, and there is no unique intersection. Now, one very important thing. The function we used earlier is not a standard line segment intersection. In that function, we only check whether the subject edge, P1 to P2, crosses the infinite line formed by the clip edge, P3 to P4. So basically, we treat the clip edge as an infinite line, not a segment. But in a standard line segment intersection, we check both T and U. T tells us where the intersection lies on segment, P1 to P2. U tells us where the intersection lies on segment, P3 to P4. For a true intersection between segments, both T and U must fall between 0 and 1. So if you want the real standard segment intersection, you also need to derive U and modify the function a little bit. Before we update the function, let's quickly derive U. We start again from the rearranged vector equation. Now we want to eliminate T. So just like before, we take the cross product of both sides with V. Now first distribute and factor. And then factor out the scalars T and U. Now step 2, kill the T term. Since a vector crossed with itself is always 0, Vxv equals 0. So we get this. Now step 3, solve for U. Here we just rearrange it. Use the anti-commutativity property. We get this final simplified formula. As you can see, the denominator is the same as the one we used for T, but the numerator is different. Now let's expand the numerator. And that's it. Same pattern as before. So now let's update our function to become a true segment-segment intersection. So this new function is different from the previous one we used in the clipping example. Earlier, we were only checking if the subject edge crosses an infinite clipping line, so we only needed T. But now we want a full, proper segment-segment intersection. And for that, we need to know what's happening on both segments, not just one. These two values give us the vector from P1 to P3, which we call R. And once we have R, we can compute U, which tells us where the intersection lies on the second segment, P3 to P4. If U is between 0 and 1, the intersection point actually lies on the second line segment. If it's outside, then the infinite lines cross, but the segments don't touch. So now we check both T and U, and only if both are inside the range 0 to 1, we return the intersection point. Okay, so that's it for this video. We explored the full code, we derived the formulas step by step, and we actually got to see how the segment intersection function behaves in real time. Hopefully, now you understand not just how the function works, but why it works, what T and U represent, why we check the denominator, and how these tiny pieces of math decide whether two line segments actually touch or not. And remember, small utility functions like this show up everywhere. A lot of the bigger, more complicated algorithms are built on top of simple functions just like this. So if you understand this foundation, then when we dive into more advanced functions later, it's going to feel much easier and much more intuitive. Anyway, thanks for watching. I hope you learned something new today. If you enjoyed this breakdown and want more videos like this, animations, visual explanations, and fun little coding tools, make sure to like the video, subscribe, and drop your ideas in the comments. See you in the next one.